Good morning. Oh, well, wait. Actually, I'm going to start. We're 3 minutes into class. Um, Hello, everyone. Good morning. I hope you're doing well. Um, so I have some announcements, but I think I'll make them in the Zoom room. So I'm just going to go ahead and get started. So today, what we are going to do, so this should be a pretty quick, easy lesson today. We are going to talk about electrical potential energy. Okay. So let me give you a formula for the electrical potential energy between two charges. All right. It is going to be K Q1 Q2 over R. Okay. And that's it. So this is one of the main formulas where Q1 is the size of one of the charges, Q2 is the size of the other, and R is the distance between the two charges. Now, what I want to point out is that this actually follows the definition of electric potential. So we have KQ1 over R times Q2. So this is the potential times, this is the potential of a single charge times the amount of charge. Okay, so this follows the definition of electric potential as well. Okay, so that's the reason why this equation is true. If you have a system of many charges, all right, what you are going to get is that the total electrical potential energy of the system is the sum of K, Qi, Qj over Rij, okay, where Rij is the distance between charge I and charge J, and we are summing over all pairs of charges, okay? So that is a nice formula. So let's do an example. Let's suppose, what shape should I use? I'm going to do let's just do a right triangle of charges. So let's suppose we have a right triangle of charges. All right. Let's say that this is this distance right here is 3 meters. This distance right here is 4 meters. Let's say that this charge is 5 times 10 to the minus 4 coulombs. Let's suppose that this charge is negative 7 times 10 to the minus 4 coulombs. And let's suppose that this one is minus 2 times 10 to the minus 4 coulombs. Okay? And by the way, because this is a right triangle, this is a 3, 4, 5 triangle. So this is 5 meters. So the question is, what is the total electrical potential energy of the system? So how many pairs are there in this system? There are 3 pairs. So there's this pair, there's this pair, and there's this pair. So this whole thing is going to get multiplied by k. So I can go ahead and just multiply this all by 9 times 10 to the 9th. So that's k. And then I have q1, q2. So I have 5 times 10 to the minus 4 times negative 2 times 10 to the minus 4 divided by 5, which is the distance between those two. And then I have plus, let's do this pair next, 5 times 10 to the minus 4 times negative 7 times 10 to the minus 4. All right, over 3. And then the last pair I have is negative 7 times 10 to the negative 4 times negative 2 times 10 to the negative 4 divided by the distance between them, which is 4. All right. Now, so if I, for example, if I multiply these two together, I would get negative 35 times 10 to the minus 8. All right. But I'm trying to cancel out this 10 to the 9th. So I'm going to write it as negative 350 times 10 to the minus 9. Okay, so then that's going to allow me to cancel out this. Okay, so I will have 9, and then this times this will be 10, negative 10 times 10 to the minus 8, so I'm going to make it negative 100. Okay, so I'm just trying to cancel out the 10 to the 9th with a 10 to the minus 9. Okay, so here I have minus 350 over 3, and then here I have plus let's see, so that's going to be 14 and then 140 over 4, like that. So then I will plug it into the calculator. And I get that the total electrical potential energy of this system is negative 915 joules. Okay? So the fact that it is negative, so if your total electrical potential energy is less than 0, then that implies that you have what is called a bound system, meaning that you have basically that the system is going to stay together. If you were to let it go, it's going to, remain stuck together there without the addition of energy. So one of the types of problems that we will often want to solve is something like this. We could ask a question where it's like, how much energy would it take to remove a charge from the system, remove it completely from the system? So what you want to do is you start out with some initial amount of electrical potential energy, okay? And you end up with a final amount of electrical potential energy. And these two are going to be different. So this is the potential energy with the charge removed. Okay. And so what we do is we do the initial energy plus the work done, which is the amount of energy it would take to remove a charge, is equal to the final energy of the system. All right. So that is the basic idea, just the conservation of energy argument for calculating the energy required to remove a charge. So let's do an example that follows that. So let's take the previous system. So the previous system had charges here, here, and here. Okay. And let's take this charge and remove it, so that the charge that was here got taken away to infinity. Okay? And then let's figure out how much work would this take. Okay? So again, we're going to use initial energy plus the work done equals final energy. The initial energy, we already calculated it. It was right here in the previous example of minus 915 joules. So we have minus 915 plus the work done. I have to calculate the final energy. So just to remind you, this was a 5 times 10 to the minus 4 coulombs and negative 7 times 10 to the minus 4 coulombs. And these were separated by 3 meters. So after this charge is removed, we remove that charge. So now there's only one pair, okay? Because the system only has 2 charges. So it's really easy to calculate the final electrical potential energy. It's going to be K times Q1 times Q2 over R. And that gives negative 1050. So we have negative 915 plus the work done equals negative 1050. All right. So then, of course, I just add that over. All right. And I get negative 135 joules is the work that must be done to remove the charge. What that means, so remember, if you do positive work, you are adding energy into the system. If you do negative work, you're actually receiving energy from the system. So what that means, because this is a negative amount of work to do that, it means that this charge wants to leave. So in other words, you would have to hold it in place. It wants to go away. All right. And I think it's pretty easy to see why. It's because this charge is right next to this positive, or this charge is negative, and it's right next to another negative charge. Okay, it's attracted to this one, but this charge is farther away. This one's 5 meters away, whereas this one is 4 meters away. So and then this is also a bigger negative charge than this is positive. So it's closer to this one, and this charge is bigger in magnitude than that one. So it would rather leave than stay. Okay? So that's why we have a negative amount of work to remove it. It already wants to leave. Okay? So basically, you could extract $135 joules from the system by letting the charge leave. Okay? So yeah. Another type of problem that I would like you to know how to solve is calculating the closest approach. Okay? So what if we have a nucleus? Okay, so this is a nucleus. Okay, and the charge of the nucleus is plus Z E. So Z is the atomic number, all right? And E is the fundamental charge, 1.6 times 10 to the minus 19 joules. Or coulombs, my bad. Okay, so if we were talking about carbon, for example, carbon has an atomic number of 6. So its charge will be 6 times the fundamental charge. All right, positive 6 times the fundamental charge. For this problem, we are going to assume that the nucleus is massive enough that it does not recoil. Okay, which is not necessarily a good assumption, but it's the one that we're going to take. And then we have another particle, and this particle has, so the charge of the nucleus is plus Ze because it has Z protons in it. And then we have another particle that is only has a charge of E plus E, so a single E, and it is coming in with an initial velocity of V initial. All right. Now what's going to happen is that as this charge approaches, because these are two like charges, there's electrical repulsion between the two. And so this charge is going to slow, and eventually it's going to come to a stop, and it's going to be sent back in the direction that it came from. Okay? So it's going to approach. It'll get some distance away. All right? And so what we want to know is, what is that distance of the closest that it gets? All right? And the problem is a little bit more complicated if we take into account the recoil of the nucleus. So that's why I'm saying let's assume that the nucleus is massive enough that it just stays put. Okay? It all right? So the nucleus has no kinetic energy. So we're going to use initial energy equals final energy. So the initial energy is, again, the nucleus doesn't have any kinetic energy because it's so massive it's just staying put. The initial energy is therefore the kinetic energy, and let's say it has a mass m, the kinetic energy of the approaching smaller charge plus the electrical potential energy. So K Q1, which is plus E, Q2, which is plus ZE, over, now what is the distance that they are apart initially? We're going to say that they start out really far apart, okay? So they're infinity apart. If you have a pie and you divide it into an infinite number of slices, the size of each slice is 0. So this is 0, okay? When this charge reaches its closest approach, it's going to momentarily be at rest. So we have no kinetic energy here, but we do have electrical potential energy. So we end up with only electrical potential energy, K times plus E times plus ZE, divided by, and then we're calling D the closest approach distance. Okay? Simplifying that a little bit, I have K Z E squared over D equals 1/2 mv squared. Solving for D, I get D equals K 2K Z E squared over mv squared. So I think this equation makes a lot of sense because what it says is that the faster the charge approaches, the closer it's going to be able to get. The more massive the approaching charge is, the closer it's going to be able to get. That all makes sense. The more charge the nucleus has, the further away it's going to go. All right? That makes sense. The more charge that this nucleus has, the more electrical repulsion it provides. The more mass and velocity the approaching charge has, the more momentum it's going to have to carry it closer to the nucleus. Okay? This type of a calculation has a ton of applications to nuclear physics. Okay? So, in particular, what if we set the distance equal to 10 to the minus 15 meters? That would be the distance at which the strong force, the strong nuclear force, is able to bind, is able to bind like charges together. Okay, the strong nuclear force is stronger than electrical repulsion, but it only works when you get really, really close, about 10 to the minus 15 meters away. So if you start this charge with enough speed where it can get to within 10 to the minus 15 meters, we could actually have fusion occurring, okay? The strong force will take over and just incorporate this particle into the nucleus, all right? Now, usually what happens is you don't control the velocity of this particle. What you control is the temperature. And the temperature, all right, is the temperature, T, is equal to a constant called Boltzmann's constant times the average kinetic energy. All right. So basically, on the left-hand side here, instead of kinetic energy, we could replace that with temperature divided by Kb. All right, and we could solve for the temperature, which would then tell us the temperature that is needed for the particle to get close enough to cause fusion. So you can estimate the temperature for fusion to occur using this equation. Now, one of the interesting things is that when we factor in quantum mechanics into account, if you were to calculate this temperature, I believe it's too big. It's too big of a temperature than what is actually observed. Okay, and the reason is that in quantum mechanics, if we were to treat this problem quantum mechanically, you can have something occurring called tunneling. And tunneling is when a particle is able to go to a location that it shouldn't be able to go. It's able to tunnel through into a region where it doesn't belong, and that sort of thing can happen in quantum mechanics. So what happens is the particle doesn't have enough energy for the strong force to take over, but then it gets close almost to the point where it could be incorporated into the nucleus, and then it tunnels the rest of the way. And so that has the effect of meaning that the particle doesn't have to get as close as you would think, because it can tunnel the rest of the way. And so fusion can occur at a lower temperature than we expect, okay? And that's a good thing. That lets the sun work, okay? Because the sun releases energy with nuclear fusion, and the sun would operate in a different way if it wasn't for the tunneling of particles. All right, so that is my lesson for today, and I will see you in the Zoom room.